Something passed through our solar system last year. That sentence sounds routine until you understand what it means. Not a comet from the outer edges of our own neighborhood, not a wandering asteroid from the belt between Mars and Jupiter. Something from another star. A traveler that formed in a planetary system we have never seen, around a sun that may not even exist anymore, and has been drifting through the dark between stars for longer than our planet has been alive. Scientists named it 3I/Atlas, and when they pointed the James Webb Space Telescope at it, what they found was not what they expected. Paul Hartog, a researcher at the Max Planck Institute for Solar System Research, put it plainly. It's really exceptional. This deuterium to hydrogen ratio in water is extremely unusual. Nobody would have expected this. For almost a century, we've assumed the universe plays by consistent rules when it comes to the chemistry of planetary formation. The same raw ingredients, hydrogen, oxygen, carbon, get stirred together under similar conditions, whether the star doing the stirring is our sun or 1/10,000 light years away. Comets, in particular, were supposed to be fairly universal. Their isotopic fingerprints, the precise ratios of heavy versus light versions of atoms locked in their ice, were understood to fall within a predictable range, shaped by similar temperatures, similar pressures, similar processes across the galaxy. That assumption formed the backbone of how we study comets. It's why scientists use them as chemical time capsules. Crack one open, measure its ratios, and you can read back the conditions of the solar system it formed in. The method has worked for decades. Then, a frozen rock from another star slipped inside our orbit, and James Webb read its chemistry. The numbers that came back do not fit anywhere on the map. Water is made of hydrogen and oxygen, but some water contains deuterium, a heavier version of hydrogen with an extra neutron. The ratio of deuterium to ordinary hydrogen in a comet's ice is essentially its birth certificate. It preserves the temperature and chemistry of wherever it formed. Cold, dense environments produce high deuterium enrichment. Warm environments weaken it or erase it over time. In our solar system's comets, that ratio is about 0.1%. In 3I/Atlas, JWST measured a deuterium to hydrogen ratio of nearly 0.95%. That's not a small difference. According to the research team, 3I/Atlas contains water enriched with deuterium at a level more than 30 times higher than any comet ever measured in our solar system, about 40 times higher than the ratio in Earth's oceans. 12 standard deviations above the mean measured across all known comets and protostars in our galaxy. Martin Cordner of NASA's Goddard Space Flight Center, who led part of the analysis, said it directly. 3I/Atlas continues to astonish us with what it reveals about the similarities and differences of its host system compared with our own solar system. And the water isn't the only problem. JWST also found that the ratio of carbon dioxide to water in the comet's coma, the cloud of gas surrounding its nucleus, was approximately 8:1, one of the highest CO2 to water ratios ever recorded in any comet anywhere. The carbon isotope ratios in those gases exceeded the range found across thousands of measured solar system bodies. All three measurements independently pointed in the same direction. This object did not come from a place that resembled our neighborhood. Scientists immediately proposed the obvious explanation: different galaxies, different stars, different chemistry. Maybe the star system 3I/Atlas came from simply had unusual local conditions, a slightly different dust cloud, a different elemental mix in the molecular nebula it was born from. The problem is the scale of the difference. The galactic variation in hydrogen isotope levels across the Milky Way does exist, but it is far too small to account for a 30-fold gap. The research team analyzed whether galactic gradients, the slow shift in chemistry as you move from the center of the galaxy outward, could explain what they saw. It couldn't. The signal in 3I/Atlas doesn't sit at the edge of the galactic distribution. It sits an enormous distance outside it. Then came the next complication. Dynamical models of 3I/Atlas's trajectory, working backward through its speed and the gravitational tugs of every star it has passed, estimate that this object has been traveling through interstellar space for somewhere between 3 billion and 11 billion years. Our Sun is 4.5 billion years old. The leading estimate for 3I/Atlas puts its age older than our solar system, possibly formed in the very early galaxy, when star formation conditions across the Milky Way were genuinely and fundamentally different from what they are today. What JWST may have captured is not an anomaly in a neighboring stellar system. It may be a direct sample of a universe that no longer exists, frozen chemistry from an era of cosmic history we can otherwise only model. That matters in ways that extend far beyond this one object. If the chemistry of planetesimals in the early galaxy diverged this sharply from what we see today, then our models of how planets and comets form across cosmic time may be missing something deep. We've spent decades building theories of planetary formation that assume reasonable consistency across different stellar environments. We calibrate those theories on what we see in our own solar system, and we project them outward. 3I/Atlas is telling us that projection may be wrong. It also raises a question nobody can yet answer. If the water chemistry is this foreign, what does that mean for the question of life? One of the reasons astrobiologists study deuterium ratios is that Earth's water had to come from somewhere: comets, asteroids, interstellar ice grains. The ratio we carry in our oceans is thought to reflect the conditions of our local origins. 3I/Atlas carries water that looks nothing like ours. Whether that makes its home system more or less likely to have supported chemistry of the kind that eventually became us is a question we don't yet have the tools to answer, and it is not the only one. 3I/Atlas is the third interstellar object ever confirmed in our solar system. The first, Oumuamua, arrived in 2017 and left scientists genuinely confused. It accelerated as it departed in a way that no known natural force fully explains, showing no cometary tail, no gas emission, nothing that should have caused the push. The second, 2I/Borisov, was more familiar. The third is the strangest chemistry ever measured. 3 visitors, 3 puzzles, each one different, each one suggesting that whatever is drifting between the stars is far more varied than we assumed. New instruments are coming. The Vera Rubin Observatory in Chile, coming fully online in 2025, will survey the sky with such frequency and depth that astronomers predict it will detect interstellar objects while they are still years away from our inner solar system, giving humanity years of warning instead of weeks. That means full spectroscopic campaigns, full compositional analysis from approach to departure, not glimpses, portraits. 3I/Atlas will be gone within years, retreating back into the interstellar dark, carrying its strange ice with it. It passed by, it let James Webb look at it, and it told us that the galaxy is not uniform. That out there between the stars, there are objects carrying chemistry we've never seen, from conditions we haven't modeled, preserving a record of cosmic history we cannot access any other way. The universe just handed us a sample from its deep past. We barely caught it in time to look. That's either the best argument for building better telescopes that has ever existed, or a sign that the next interstellar visitor, whenever it arrives, is going to make this one look familiar. See you in the next one.